So now that we know how monads are able to handle side effects, we can try to write some computations using the features that the monad type class gives us. And let's start by writing a very simple function. Here I wrote a function that I called add logger2, and well, I'm working with logger here since it is an instance that we constructed in the previous exercise video, so we know how it is implemented and how it works in reality. And this function is just taking a logger which contains the number, unwrapping it, adding 2 to the number, and returning a new logger. And there is nothing special in this expression. In fact, we could have written the same computation using the fmap that every functor has to implement with the function that we get by using partial function application with the plus operator. So in order to make a bit more exciting what we are working with, let's just add a little side effect. And in order to do so, I'm using the log message function that just creates a logger which contains the given message as input with no real value, since we are only interested in the side effect, and then sequencing it with the return value so that we keep the side effect and the value we are interested in. And well, of course, this computation could have not been written using only functors, since those cannot handle side effects, but could have been written by using just an applicative. In fact, as we see, this expression is creating a +2 function that works with applicatives and applying it to the logger with a default value. And then we are using the log message functions, which doesn't really return anything, but since we are using const, it doesn't really matter. And this works just fine. So this same expression could have been written in an applicative way. So let's actually write a function that depends from intermediate results. So here I am defining a function that I called noisy add and then square, which given two loggers that contains numbers will return the square of the addition. That of course will contain as number the result of squaring the addition of the given two logger. And first I am extracting the value we have in the first logger. Then I am doing the same with the second logger inside the lambda, which is provided as second argument to the bind operator. And this is because if I were to do something like chaining the resulting monad of this expression, we have no more access to the value that was wrapped inside the first logger. So in order to have access to both the value of the first and the second logger, we have to create a new expression inside the lambda. So we are using nested lambdas in order to access multiple values of multiple loggers. And well, as it is written here, this is doing the job, but this function is called noisy. So let's add some side effects. And here I am logging the input of the first logger we have and doing the same with the value of the second logger, and then adding the intermediate results. So these lines are just noise. This is the actual computation that we are doing. In any case, if we are using monad, it is because we are also interested in side effects, and we see that when we start to write more complex computation, we have to use quite a lot of syntax. We have a lot of binds, sequences, also the lambdas, so there is quite a lot going on here. And imagine having a really complex computation. This kind of syntax can get pretty annoying very quickly. Fortunately, since working with multiple values extracted from computations that can have side effects is something that occurs frequently while writing programs, Haskell does already have a solution for that, and that solution is to use what is called the do notation. Now, we use the do notation by, well, as you can imagine, writing the do keyword. And what this does is just making available this kind of syntax inside the expression that follows that do keyword. And this syntax is just writing a left-facing arrow with a monad, which we assume contains a value, on the right side of this left-facing arrow, and then unwrapping the value and storing it inside this variable. So in order to extract the value, we have to perform whatever computation this monad is representing, since a monad can have side effect and the resulting value may change depending on the side effect. We have to run the computation, as we see as an example when using the bind operator. The result of a monad can be, yes, just a simple monad itself, but well, we know that this whole expression evaluates to a monad. So a monad can also be an entire computation, which may have side effects, and in some cases, the ending value, well, not in our case, but in some cases, the ending value may depend on the side effects. Therefore, in order to execute this line, the monad on the right has to be executed, and once it has been executed, then we have a value, and this value is then stored inside, well, whatever variable we have on the left of this operator. And this syntax that is possible thanks to the do keyword allows us to use a plain Haskell value, much like we do when using the lambda. Here we have a plain Haskell value. Well, in this case, when we do this, it's kind of wrapping whatever follows inside a lambda so that we have that variable available in the rest of the do block. Another advantage of the do block is that you can imagine each line to be separated by the sequence operator, since when using the do, each line is executed before the following one, therefore acting as if there was a sequence operator in between, since of course do is meant to handle side effects, and in order to have side effects, we have to be sure on the order of the execution. And then, just to let you know, it is also possible to use pure function inside a do block, just as we can use pure function inside a lambda. There is actually no difference. And if we were to store the result of a pure computation, we can use the let keyword before the variable that is holding the result of a computation, and then here we are just adding some more noise. And unimportant, not so much a detail, is that every do block has to end with an expression that evaluates to a monad. And well, this is not actually a problem, since return works for every monad and GAC is able to deduce what monad we are working with. And this thing of having a monad as last expression is what allows us to work with raw Haskell values inside a do block, since as long as we are in a do block, we can do whatever we want, but we have to provide back that monad so that we can keep track of the possible side effects that we had in this do computation. And let me show that there is actually no difference between this function and the version with the do, apart of the code being much more clean than the nested lambda version. In any case, here I'm providing 2 and 3, and the expected result is 2 plus 3, 5, and then 5 squared, 25. And we see that the computation goes through smoothly, and we also got the side effects, and we can perform the same computation using the do version, and we see that we will get the same result because both are sequencing monadic computations, extracting values, and returning a monad. So in this video, we had a look at a practical example on how to use our logger monad. We saw how it is possible to access multiple values wrapped inside multiple monads using nested lambdas, and we also saw how the do notation allows to express the same logic in a cleaner syntax, allowing us to work easily with monads. And with what we learned in this video, in the next we are going to see a very important monad that allows us to write programs in Haskell. In any case, I want to thank you for your time. Remember to stay decentralized, and I will see you in another video. Bye bye.